Hi guys, today we're going to go over section 5.8, Kinetic Molecular Theory, to section 5.10. Kinetic molecular theory is for ideal gases. These are the 5 postulates or rules of kinetic molecular theory. Number 1, particles of gas are in constant motion and collide with both one another and the container. 2, the gas is mostly empty space. 3, pressure is exerted when the particles hit the sides of the container. 4, we assume the particles do not interact with each other. And 5, the average kinetic energy of the particles is proportional to the temperature. So the bigger the molecules, the slower they move. Since kinetic energy is 1/2 mv squared, if the mass goes down, the velocity goes up. We'll see that in a simulation in a minute. So if we had to boil down an ideal gas law, what is an ideal gas? These are the 3 main points. Number 1, the volume of the gas particles is negligible, meaning a tiny helium atom is going to act the same as the much larger carbon dioxide, which is like 11 times bigger than the helium. But we assume that they are so tiny and so far apart that they are going to behave the same way. Number 2, there's no forces acting on the particles besides their collisions with each other and the wall. So there's no gravity acting upon these gas particles, and there's no intermolecular forces between them. Number 3, collisions are perfectly elastic. Anybody that's taken physics has probably learned about elastic and inelastic collisions. That just means when they bounce into each other, energy is transferred completely from one to the other, and no energy is lost in that collision from heat or some other way. Most real gases behave close to ideal at STP. So the laws that we learned that require that it be an ideal gas, those are all pretty good assumptions for our chemistry classroom. Here's Boyle's law, where we're studying the volume and pressure of the gas. And this is what it would look like if we were looking at it from the lens of kinetic molecular theory. They're in constant motion, they're colliding with each other, and there's no forces in between these little red particles. If you decrease the volume, so here's our piston, if the piston goes down, so the volume is less, then the pressure inside that container is going to increase due to the increasing number of collisions with the smaller surface area inside the container. And so we get Boyle's law, which is P1 V1 equals P2 V2. And this is an inverse relationship. When the volume went down, the pressure went up, versus Charlet's law, where we have an increase in temperature. So this picture on the right has a higher temperature. That's what the 3 little flames underneath are showing us. And when the piston is allowed to move, it's going to rise, meaning there's a greater volume with a greater temperature. They're directly proportionate. So the temperature goes up and the volume goes up, and vice versa. If we took a balloon or if we cooled this container down, then the volume will decrease with that lower temperature. And that's also due to collisions, because when you heat them up, this little line is showing that they're moving faster. And if they're moving around faster, then they're going to collide more frequently and with greater force with the inside of the container. Avogadro's law has to do with the number of particles, or the moles of particles. So we've doubled the number of little blue particles inside. Notice they're moving at the same speed, so they have the same temperature, and pressure is the same. So if we double the number of particles, then the volume doubles. Those are directly related. An increase in moles equals an increase in volume. Okay. Oops. And vice versa. If you have balloons filled with hydrogen, nitrogen, and oxygen, if they're all exactly the same volume and they're at the same pressure, room pressure and room temperature, then we know that there's an equal number of moles inside each balloon. This is Dalton's law according to kinetic molecular theory. The particles have negligible size and they do not interact. Consequently, the only property that distinguishes one type of particle from another is its mass. But even particles of different mass have the same average kinetic energy because of what we said earlier. The smaller ones will be moving faster and the larger ones will be moving slower. So they exert the same force on the container. Thus, adding components to a gas mixture, see we have two separate gases, hydrogen and helium, and then we've mixed them together. Adding components to a mixture, even different kinds of gas, has the same effect as simply adding more particles. The partial pressures of all the components sum to the overall pressure. So we can add the pressure 2.9 and 7.2. When we mix them together, we will get the total pressure of those two added up. All right, so you will see these graphs a lot on the AP test and in this section. And it is a graph of velocity versus the number of particles. It's a very misleading graph, and a lot of times people are confused because what is on the y-axis is actually the number of molecules, and the velocity, we like to think velocity is on the y-axis, and the number of particles is on the x-axis, but it's actually reversed. So this tallest peak, the red peak, is for oxygen O2, which happens to be the largest particle here. And so it's the biggest particle, therefore it's going to be moving the slowest. So velocity along the x-axis, little hydrogen over here, they're moving a lot faster than all the other particles. Oxygen has the lowest velocity, and the peak, the highest peak, this red one, is due to the biggest number of molecules that are traveling at that very slow speed. Okay, so they're about, I would say, 400 meters per second, whereas hydrogen here, the average, that peak for hydrogen is about maybe 16 or 1700 meters per second. So they're traveling much faster. And that is again due to the definition. So kinetic energy is 1/2 mv squared. And this is actually the Greek letter. So this is our mass of the particle, and this is velocity of that particle. And if they have the same temperature, same T equals same average kinetic energy. So they have the same energy, all of these particles in this description, because they're all at 25 degrees Celsius, according to the little description down here. They're all at 25 degrees. So they all have the same average kinetic energy, but their masses are different, and therefore their velocities are going to be different. So a small mass, for example, H2, which has a mass of 2.02, equals a very high velocity. And a large mass, like O2, for example, is going to lead to a very low velocity. So oxygen, again, the peak, the average would be about 400 meters per second, whereas helium, the average is about 1600. So 4 times the velocity of the oxygen. Okay, so this diagram over here is showing the higher the peak, the more molecules there are traveling at that speed. So helium, there's a wider range of their velocities, but overall, the helium atoms are traveling much faster than all the others. Okay, I think I said helium. Helium is traveling faster than all the others, but hydrogen beats helium. There's a greater area over here under the green line, showing that these are traveling much faster than the helium atoms even. Okay, so another way to look at this is we have different temperatures. So what is this showing? The red peak, again, has the lowest velocity. So these are the slowest molecules, even though there are more of them traveling at that slow speed. They're going slower. And the yellow is going to be the fastest. Okay, so these are traveling the fastest. All of this area that is not underneath the green, these are all moving at a faster velocity. And so which types of particles travel faster? If this is all one thing, so let's pretend these are, oh, it says right here, these are all N2 molecules. So everything is nitrogen. But at a higher temperature, there will be more particles traveling at these higher speeds. And that's 2000 Kelvin. That's an incredibly high temperature, 2000 Kelvin. Okay, so the colder the molecules, the taller the peak, but the farther it is to the left, which is a low velocity. The higher the temp, the smaller the peak here, and the greater the average velocity of those guys. The reasoning behind that has to do with calculus. So the area under the curve has to be the same. The total number of particles is the same for all of these peaks, but we have a greater range. So that's why the yellow is more broad than the red is. You don't need to know calculus to get the graph, but that is the reasoning behind it. Okay, diffusion and effusion. I have some still images here. We're going to look at these different particles. So blue is the larger particle and red is the smaller particle. We have a divider between them. When we remove the divider, we're going to see how the two interact with each other. Okay, and diffusion is just the mixing of the two different gases because of their random constant motion. Okay, so, this is actually going to show you, going with our kinetic energy, backing up a little bit. These blue particles are a lot bigger. Notice that there are 478 of those heavy particles, and their average speed is, right here, 460 on average. Okay, and this would be the graph of the number of particles versus their speed. Now let's look at a little tiny red particle. Same pressure, same number of particles, same temperature of 300 Kelvin. And this is what those red particles look like. At 300 Kelvin, you can see their average speed is over 1200. And notice that this graph is more broad, it's more spread out. And so their average is much higher of 1200 compared to the blue. Same number of particles, just this time I did the light. Okay, same pressure and same temperature. And clearly they're moving a lot faster. But because of their low mass, they had to have a much higher velocity to keep that energy balanced. This is the diffusion. So along those lines, we have the blue particles that are moving very slow because they're very big, and these little tiny red particles bouncing around very quickly because they're very small. They are at the same temperature. They're both at 300 Kelvin again. And when I remove the divider, I'm actually going to click this slow button. Let's slow them down so we can watch it for a minute. Remove the divider, and you'll see a lot more of the red is going to reach the left side before the blue reaches the right. Okay, and why is that? That's because they're traveling at a much higher velocity. Since they're traveling at a higher velocity, they're going to diffuse more quickly than the blue. And let's see, what's the data show us? So far I have 17 red on the left, and I have 10 blue on the right. Okay, if I speed them up, so it's normal speed, let's see what it looks like. They're moving a lot faster. Okay. And if I pause right here, whoops, pause right here. They're actually about quite even, but that is the definition of diffusion, is the mixing of the two gases. At the very beginning, we saw that the red gas diffused faster than the blue gas because of its temperature, but they will eventually reach a balance point where they are at equilibrium. And remember, equilibrium means equal rates. So if I show the particle flow rate, these arrows are about the same size, the red to red and blue to blue. So if they're going to the left and right at the same rate, which it appears they are, then it's at equilibrium. So it looks like it's at equilibrium. Let's see. Yep, so the arrows have balanced. If I reset the divider and then remove it with those arrows, you'll see how it starts out, and then they move back and forth until we get to that equilibrium point. All right, so that is diffusion. You can see they were separated, they began mixing, and they were fully mixed. Why are they mixed? Because of their constant rapid motion. All right, and effusion with an E is very similar to diffusion. The same rule applies. The smaller the particle, helium, the faster it will effuse and diffuse. And effusion is just you have a box, you have a hole, and the gas is going to leave through that hole. So the smaller the particle, the faster it will leave. The bigger the particle, like this ethylene oxide, the slower it will effuse and diffuse. A good example would be a helium balloon. The reason the helium balloon goes flat is because there are tiny pores in the balloon that the helium can pass through, and so they will escape, leaving only the bigger particles, the carbon dioxide and the oxygen and nitrogen behind. Okay, real gases. Gases behave ideally, this is a quick reminder, when the volume of the gas particles is so small compared to the space between them that we get to ignore the volume of the particle, and the forces between the particles are not significant. So there's no significant intermolecular forces. There are no force pulling the little particles towards each other. Most gases behave close to ideal at STP, but these assumptions break down. They no longer apply at very high pressures, because when you put a gas under a very high pressure, so picture this situation, if we increase the pressure and push them way down, the space in between the particles compared to the size of these particles it now cannot be ignored. It's no longer negligible. The other time is if we cool them down to a very low temperature, below freezing, and we want them really, really slow. They're going to be close enough together and moving slow enough that when they collide, they could actually stick together and start to condense. So at very low temperatures and at very high pressures, the ideal gas behavior starts to break down. Okay, and so we have real gases. This equation looks scary. We're not going to have to actually calculate anything, but we need to know that when it's a real gas, the pressure may be lower than expected because of the forces of attraction between the particles. So because they're pulling towards each other, there's less pressure of collisions on the container. And so in the van der Waals equation, this is how we correct for that. The lower than expected pressure, we have to add a correction value to that. Also, real gases have a volume that is greater than expected because we now have to worry about the volume of the particles because there's so little space in between them. And so you'll see, since the volume will be greater than expected, we're subtracting a correction from the volume. Okay, and then at ideal, it's just P and V equals nRT. The van der Waals has those added parts that are the correction. We will not be using this equation again, so don't worry, but you do need to know that real gases have some intermolecular forces and their volume is not always negligible. Okay. All right. I hope you guys have a great day. Bye-bye.